Definitions. Everybody knows what gravel is? Bunch of stones. And if you have some sort of conveyor belt right here, and it's running your gravel up and falling down, it will form a beautiful conical pile. Okay? A conical pile is a pile in the form of a cone. Okay? Draw this here to help visualize it even more. A few little stones will fall over here, but that's okay. Okay, so it makes sense that you would have a situation where this is traveling at a constant rate and you have the same amount of gravel traveling up that conveyor belt. And what's going to be happening here is your pile is going to be getting bigger and bigger and bigger. Now they're saying right here that our diameter is always double our height. Maybe I didn't draw a perfect diagram. Diameter is always double the height. So we've got a relationship there as part of our conical pile. We want to find the rate of change of the height. So we want to find dH dt. So that tells us that height is a function of time, which makes sense. As time goes on, that cone is going to get taller and taller and taller. And we want to find that exactly when the height is 3 meters. Now they're telling us that it's falling on the conical pile at a rate of 4 meters cubed per hour. So we need to say, well, what kind of relationship is that? That some change of something per time is going to be 4. What is that? Is that a radius? Sorry? It's a volume. And it tells us, we kind of get a hint with the meters cubed per hour, because what's on the bottom is your change in time per hour, and the meters cubed is a measurement for volume. So we also know that volume is a function of time. So now we need to come up with the equation that relates these two things. Do we have a volume formula for a cone? Yes. Do any of us know it? No. Okay, how do I remember the volume formula for a cone? First of all, I know the volume formula for a cylinder. Do you know the volume formula for a cylinder? The volume formula, height times pi r squared. And the reason for that is if you wanted to build your own cone out of paper, you could. You just have to cut a circle out of one piece of paper, then take another piece of paper and cut out another circle, and keep adding those circles up for hours, and you would make a perfectly filled cone. That's the basic idea for the volume of the cone. It's the same idea for any prism. You take the area of the bottom and multiply it by the height, and that gets your volume. It wouldn't have a height, but it's the idea of sort of like a limit going to 0 that would account for all of those volumes going up. And that adds, and then when we get our height, I mean, with the paper it has a slight width, so you really can see it. Calculus would say, well, that's not perfect, but if we kept going to smaller and smaller heights, we would just add more of those, and that eventually would make the volume anyways. Now, a cone is less than a cylinder, but related to the cylinder. And the volume for a cone, and I don't have a really good way to say why it's a third. I wonder if you opened up a cone, if it would make, you know, when you open up a cone, you get a sector of a circle. Have you ever done that? Taken a cone and cut it and opened it up, and you get a sector of a circle. I wonder if that sector of that circle is a third of the whole thing. Maybe, maybe not. No, it probably depends on how narrow the cone is. Yes? Yeah, maybe it's a triangle thing, has 3 sides. That's a good way to, I like it. Yes?
So therefore our surface area be 2 over the 3 pi h.
Ooh. Well, but you have to be careful because when you do the derivative of that, there's 2, the r and the h. So just taking the derivative won't be that easy. But we could look if we could do it with product law. But we'll look into that. Okay. So now we've got our volume thing, and the same problem with figuring out the surface area with the derivative is we have 2 variables right now. We have radius and height. Okay? And we don't have any dr dt, even though we know that the radius 2 would be a function of time, and so on and so forth, but we don't have any information about that. However, we did know that the diameter was 2 times the height. So if there's a relationship between diameter and height, there would also be a relationship between the radius and the height. In fact, in this particular example, the radius and the height will always be the same then. Because if the diameter is always double the height, the radius and height would be the same. So what that allows me to do is to take my volume formula, and instead of writing r, I can replace that with an h, and if I have h squared times h, I'll get h cubed. So now I've written an equation that just relates volume and height, and because of that, I can take the derivative with respect to time, bring the 3 out in front, which cancels out the 1/3. And we're told 4 meters cubed per minute at a height of 3. And dH dt was also 3? No, dH dt is what we want to find. So dividing both sides by 9 pi. Would tell us that when the height got to 3 meters, oh no, sorry, yeah, when the height got to 3 meters, okay, at that specific time, the height was changing at a rate of 4 over 9 pi. What units were we using? We should put the units in. 4 over 9 pi meters per hour. Which could give the person an idea of, do I need to move my conveyor belt right away, or how much time do I have before I need to move something like that? So again, we have a perfect sphere of snowball. It's melting in your hands perfectly. Your hands aren't contributing to any of the melting so that it's melting perfectly on all directions, so it's slowly getting smaller while maintaining its ideal sphere, just for this math problem. And we know that the volume, dV dt, is decreasing at a rate of 1 centimeter cubed per minute. And since it's decreasing, we might put a negative there. Okay? We can put a negative there, or we could solve this without our negatives and then just talk with increasing and decreasing at the end. At what rate is the radius, what is the change in radius with respect to time? That's what we want to find when the radius is 5 centimeters. So at the specific time that the radius is 5 centimeters. How big was this snowball to begin with? 10 centimeter snowball? That's pretty hefty. So we know that volume is a function of time, and we know that the radius is a function of time. And we already discussed in the question before, the volume of a sphere is 4/3 pi r cubed. So then we can use implicit differentiation, take the derivative with respect to time. And dv dt is -1. We're finding it when the radius is 5. 5 squared would be 25 times 4 is 100 pi r dt. And so the radius is changing at a rate of -1 over 100 pi. That would be -1 over 100 pi centimeters per second. What's that? Is it per minute? Yeah, it's per minute. Thank you. Then it's not melting so fast. Whew. Yes.